Hello, everyone.
All right. So, for Coach, just a few questions before we start. So, have you seen the new assignments? I've published them today. Have you seen, yes or no? Perfect. Second question: do you receive an email when a new assignment is published? You receive an email when a new assignment is published. Is that a yes for my the second question? Okay, you receive an email. Perfect. Now, another question: do you receive any notifications that are not addressed to you? So, for example, notifications that are meant for another group, or I don't know, a different tutor sends a notification to their group, but you do. All right. Okay. Okay, I'll look into that. The ones for year groups, yes, of course, but the ones for other tutors. Okay, so could you please email me and say, so I want to investigate. So email me at at physics box UK. Can you please email me and say, I am in group so-and-so. I receive emails from another tutor, group so-and-so, or I don't know who it is, but I receive them. Okay, so just let me know so I can investigate further. So that if we have something broken in the system. Well, no, if you're in a support group, then you should. Oh, you're not in a support group, but you receive notifications. Yes, please let me know. So basically, if you receive notifications, anything other than what you're supposed to receive, then please let me know. Okay, so let's get started. Today is an exciting topic. It's sequences and series, and sequences and series. And I'm going to talk about. First, I'm going to talk about geometric sequences, geometric series, and then going into Taylor series. We've done, me and David, we've done several webinars on this topic. So please refer to those. And otherwise, yeah. So this is new material today. So let's have a go. I'm going to share my screen. Okay. First question is look at problem 2. Look at problem 2. So let's have a look at problem 2 first. This is a Google interview question, allegedly. I have no way to prove whether it's a Google interview question, but it is an interview question. Certainly. Imagine a country where every family wants to have a boy. If the first baby is a girl, then the family has another baby, and then again until a boy is born. Okay. They stop having children once a boy is born. So effectively, every family has a boy. And yeah. Do you think you will have more boys or more girls in this country? What do you think? More girls. More boys. Interesting. More girls. Equal. All right. Can somebody argue either way? Girls, because there's a possibility of family having infinite amount of girls. Yes, that is true. Certainly, you can have infinity girls. Sanjibatis thinks it's equal, though. Yeah, because on the one hand, every single family will have a boy. But on the other hand, you could have infinity girls. So probability doesn't change. Good. That is a perfectly valid point. Okay. So we'll come back to that. You would only have as many boys as families. That's another point. You would have as many boys as families. So if you have 10 families, you have 10 boys. But you're not limited to just one girl. So you might have more girls. So 10 families means 10 boys, but how many girls? Ah, that's the question. So what's the average number of girls per family? That's what we need to calculate. Or, in other words, what is the expected number of girls per family? And this is what we're going to talk about. We'll get back to that. So let's quickly recap the formulas for arithmetic and geometric sequences. So have you studied this topic in school, arithmetic and geometric sequences? Arithmetic and geometric sequences. Yes. GCSE, okay. Just so today, okay. Very good. Done arithmetic, but not geometric. So the only certainly no is from Tom. Tom. So have you not done anything like that? Anything of the sort? Any sequences, arithmetic or geometric? Or have you not heard of them? I'm just feeling the crowd. Where should I start with? Can I assume some, not further than just, but you have understanding of what it is. Okay. Okay, so that's nice. So if an arithmetic sequence is when you add the same number. So for example, 3, 7, 11, 13. Oh, what? Not 13, certainly. 11, 15, etc. So this is an arithmetic sequence. Arithmetic. As opposed to geometric. For example, 2, 4, 8, 16, 32, etc. That's a geometric sequence. Geometric sequence. Now, the first term we call the first term A. Is the first term. D is the common difference. UN is the nth term. And Sn is the sum of the first n terms. And the formulas are as follows. The nth term is the first term plus n minus 1 times d. And it makes perfect sense because you have, if you want to find term 4, you need to make 3 steps. 3 times you need to add d 3 times. So that's why it's n minus 1, because n minus 1 steps takes you to un. And the sum of the first n terms, I really don't want to derive these formulas. The derivation of these formulas has been done before in the previous webinars, but it's a very common thing to do. So I'll just give you the formulas without derivation. Sn, there are 2 formulas. So for example, first of all, it's 2a plus n minus 1d divided by 2 and multiplied by n. That's the first. Well, it's usually written slightly differently, so let's. Or you have Sn equals n over 2 multiplied by the first term plus the last term, which makes perfect sense. First term plus last term divided by 2, that gives you the average. That's the average of the, that's the, average. And then multiplied by n, that gives you the total. Does this all make sense to you? Do I need to, especially those who haven't done arithmetic sequences? The second formula, if you have a sequence, so for example, 3 plus 5 plus 7 plus 9 plus 11, what you want to find is the total. So the total is the sum. So you take the first term and the last term, 3 plus 11 divided by 2, and that gives you 7. That's the average. That's the average value of the terms. And then you just multiply by n. So n multiplied by 7, which is 5 times 7. 5 times 7 is 35. And that gives you, that's the total. So the answer is 35. And the thing is, it works beautifully. For example, if you want 3 plus 4 plus 5 plus 6 plus 7 plus etc. plus 2008, right? It's very easy. You take the first term, you take the last term, so 3 plus 2008, divided by 2, which gives you the average, and multiply by the number of terms. So this is where you need ingenuity to find the number of terms. So 2008 minus, it's not as easy as doing 2008 minus 3, because that doesn't give you the true number of terms. That gives you 2005. That's 2005 steps. So that means that there are 2006 terms. 6 terms. Because you have to consider the first and last as well. Well, the first term as well. So multiply by 2006. So this sum will give you 3 plus 2008 divided by 2 multiplied by 2006. So 2,017,033. 2,017,033. But you can also do that using the other formula. So Sn is equal to 2a plus n minus 1d divided by 2 multiplied by n. So that is 2006 multiplied by 2 multiplied by 3 plus 2006 minus 1 times d times d is 1 and divided by 2, which should give you the same answer. 2006 multiplied by a fraction 6 plus 2005 divided by 2. You do 2,017,033. 2,017,033. Does it make sense? Do all three formulas make sense to you? Please let me know, especially if you haven't done this topic. Okay. The geometric sequence, you have the first term is usually A or B. So A, let A is the first term. R is the common ratio. Is what you multiply by every term. So here you multiply by 2. So the common ratio is 2. So the first term is 2, and the common ratio is 2 as well. So UN is, of course, the nth term, and SN is the sum of the first n terms. Okay, so let's say you have UN. So UN, well, you take the first term and you multiply by R, right? So the first term is A, the second term is AR, the third term is AR squared, the fourth term is AR cubed, etc. So U1 is A, U2 is A, U3 is AR squared, U4 is AR cubed. So carry on, and UN is going to be AR n minus 1. And that's the formula. AR n minus 1. Actually, you know what? I want to do the sum. I want to do the sum. And because it's so elegant. So to do the sum, I write it down first. The sum of the first n terms is going to be A plus AR plus AR squared plus etc. plus AR n minus 1. Now, this is the sum of the sequence, right? So I hope everyone understands the sequence, because yeah, do you have are there any questions? Is there anything you don't understand about what's written on the screen right now? Please let me know, because if you're not clear, you'll have real trouble understanding later on. I'm happy to explain. Please be honest if there's something you don't understand. How come the first term of the arithmetic sequence was AN? The nth term. Aha. Okay. That's a very good point. So when you do 3, I don't know, 7, 11, 15, etc., the nth term can be given by the formula an plus b, right? And in this case, it's 4. It's 4n minus 1. It's 4n minus 1. That's what you've been taught at GCSE, right? Is that what you're asking, Archie? Now, if you apply the formula, un is equal to a plus n minus 1 multiplied by d. Let's see what do we get. A is 3 plus n minus 1 multiplied by d. D is the common difference. It's the 4 multiplied by 4. Expand. 3 plus 4n minus 4, which gives you 4n minus 1. Okay? So it's two different ways of doing the same thing. So yeah, it's just the arithmetic sequence is a more formal approach. The formula is a more formal approach. Okay, so here the first term is a. To get the second term, you multiply a by the common ratio, which in this case is 2. So in this sequence, the first term is 2. The second term is 2 multiplied by 2. The third term is 2 multiplied by 2 squared, etc. So yeah, that's what it is. Now if you write down u1 is a, u2 is a times r, u3 is a times r squared, u4 is a times r cubed, etc. And then you write out the sum. What I'm going to do next will shock you. No, won't shock you, but hopefully pleasantly surprised. Pleasant, oh, I don't know, please you. I'm multiplying by r. The whole thing. I multiply the whole thing by r. I get r Sn is equal to ar plus ar squared plus ar cubed plus etc. The last one is going to be arn. I just multiplied the whole thing by r. What I'm going to do next is I'm going to subtract. I'm going to this minus this. So I'm going to have r Sn minus Sn on the left. I subtract the left-hand side from the left-hand side. And here, if you see, it's AR minus AR, so this will cancel. AR squared will also cancel. AR cubed will also cancel. Everything will cancel except this term and this term. So what you will have is ARN minus A. I factorize the left and right. So Sn R minus 1 equals A Rn minus 1. Just factorize. And now I make Sn the subject is A Rn minus 1 divided by R minus 1. That's the formula for the sum of the first n terms of a geometric sequence. And interestingly enough, some sequences are infinite. Yeah. So some sequences are infinite. Geometric sequence. For example, 1/2 plus a quarter plus an eighth plus 1/16 plus etc. up infinity. Or actually, you know what? Not even that. 0.3 plus 0.03 plus 0.003 plus 0.0003, etc. What would that be? It's going to be 0.3333, which is 1/3. So you imagine you take a glass and you pour 0.3 liters. It's my marker. Can't find one. Anyways, imagine you pour 0.3 liters of water into the marker, into the, so here. So you take a cup and you pour 0.3, so 0.3. Okay. Now you add 10 times less. And it's going to be 0.33. And you add 0.0003 liters of liquid, and it's going to be 0.003. You keep adding water to the cup infinitely many times, and you will end up with 1/3 of a liter. You will end up with a finite amount. If you keep adding water infinitely many times, a non-zero, you keep adding a non-zero amount of water infinitely many times, and yet you end up with a finite amount. And that's quite cool in terms of we say the series is converging, and it's equal to 1/3. Now, if you take 1/2 plus 1/4 plus 1/8 plus 1/16 plus etc., well, this is very easy to visualize. You take a square. The area of a square is 1. Area of a square. You cut the square in half, and this is a half, and this is a half, of course. Now you cut this part in half, and that makes it a quarter. So half plus a quarter. Now this part, you cut it in half as well, and this is 1/8, and this is 1/16. This is 1/32, 1/64, 1/128, etc. So you end up with 1 because you're adding infinitely many rectangles, and the sum is 1. Okay. This only works if r is less than 1. So if modulus r is less than 1, then the sum to infinity is equal to the limit as n tends to infinity of Sn, and that is equal to the limit n tends to infinity of a Rn minus 1 divided by r minus 1. And because r is less than 1, r to the power n tends to 0. Raghav, yes, it does reach 1. Well, I mean, after it reaches 1 after infinitely many steps. This tends to 0 R is the common ratio. R is the common ratio, is what you multiply by every time. So if you multiply by 2, of course, the sum to infinity is going to be infinitely large. But if you're multiplying, and like in this case, R is 0.1. You're multiplying by 0.1 and 0.1, which is less than 1. And here, you're multiplying by 1/2, 0.5, which is also less than 1. Modulus of R just means that if it's negative, so for example, you can have 1 minus a third, a ninth. So that means R is minus 1/3, but modulus R is still less than 1. Because modulus of 1/3 is less than 1. Yeah, does that make sense? Thank you for asking these questions. Thank you for asking these questions, because that's important for understanding. Okay, R is what you multiply by. So if you have a geometric sequence, for example, 1 minus a third, a ninth, minus 1/27. R is what you multiply by every time. So here you multiply by minus a third. Here you multiply by minus a third. Here you multiply by minus a third. So this number is called R. So R is minus 1/3. The modulus of R is equal to the modulus of minus a third, which is a third, because the modulus of minus a third is a third, and that is less than 1. Does that make better sense? Does that make more sense? R is the common ratio. Yes, exactly. If R was minus 2, it wouldn't work. So for example, even though minus 2 is less than 1, but modulus minus 2 is greater than 1. Therefore, it doesn't work. Doesn't work if R is equal to minus 2. And you can easily verify that. 1 minus 2, 4, minus 8. Well, 1 minus 2 plus 4 minus 8 plus 16 minus 32 does not have a finite sum. Yeah, it's just nonsense. It's a diverging. Yes, so effectively it can only be converging if R is less than 1 by modulus. And because R is less than minus 1, R to the power n, because anything less than 1 to the power n becomes smaller and smaller and smaller. So we say it tends to 0. And because it tends to 0, the limit is when this becomes 0. It's a 0 minus 1 divided by r minus 1, which is minus a over r minus 1, which is a divided by 1 minus r. And that's a very powerful formula. The sum to infinity is a divided by 1 minus r. But it only works if r is less than 1. Is modulus r is less than 1. So let's test that formula. For this sequence, r is 0.1, and A is 0.3. So sum to infinity should be A divided by 1 minus R. This should be 0.3 divided by 1 minus 0.1, which is 0.3 divided by 0.9, which is 3 over 9, which is 1/3. Works. And here, once again, the first term is 1/2. The common ratio is 1/2. So the sum to infinity is A divided by 1 minus R. So it's 1/2. 1 minus 1/2. So it's 1/2 divided by 1/2, which is 1. So sum to infinity is 1. So it works. The formula works. If it has a finite sum, it is converging. If it does not have a finite sum, it is diverging. So basically, a geometric series is diverging if R is greater than 1 or less than -1. Okay. So I hope that makes more sense now. So let's write down the formula as well. Sum to infinity is A divided by 1 minus R. Beautiful formula. Any questions? Any questions about the formulas? I want you to understand these three formulas. This is the most general formula, but I mean, this formula is quite general because it works for all geometric sequences. There isn't a standard formula that you can use. No, there's it's like integration. You have to use quite a lot of ingenuity to add them all up, as I will demonstrate. In the next question. I think the most important thing is that you understand that this is true, because we will be using this a lot today. Yes, Resham, you can rewrite it as that, as you said, exactly, because you're just multiplying the top and bottom by -1. So you can rewrite it as A 1 minus Rn divided by 1 minus R. Okay. So back to the Google interview question. Imagine a country where every family wants to have a boy. So let's find the expected number of boys and girls. Well, every family will have exactly one boy, so the boys is easy. The expected number of boys is exactly equal to 1. So now let's write down the probability of number of girls. So the G is the number of girls, and here we'll have the probability of number of girls being equal to this. So you can have 0 girls, you can have 1 girl. Let's find the probability of a family having 0 girls. And then find a probability of family having 2 girls, 1 girl, 2 girls, etc. 3 girls, etc. Okay, so for this one, we're going to use a tree. So the first baby is either a boy or a girl. So the probability that if it's a boy, that automatically means that there's 0 girls. And the probability of this event is 1/2. So the probability of having 0 girls is 1/2. Because a family starts having babies, a boy is born, that's it. That's half. That's 50%. There's a 50% chance that the family will have 0 girls. Is that clear? Is that understandable? Any question? Now, there's a 50% chance that it is a girl, therefore, the family will have another child. And again, it's either a boy. In this case, there is 1 girl in the family. So there's a girl and a boy. So here is just a boy. The outcome is a boy. The outcome is a girl boy. And here it could be a girl again. Now the probability of this is a half and a half again. So half times a half, the probability of this event is a quarter. And this is a half. So the probability of having 1 girl is a quarter. Now, if the family has 2 girls, then they will have another baby, and that will make it either a boy or a girl. So it could be a girl, girl, boy. Now 3 kids in the family, girl, girl, boy, but the probability of that is 1/8. So the probability of having 2 girls is 1/8. And well, yeah, I think you can see where this is going. So half, an eighth, 1/16, etc. So 4 girls, the probability of having 4 girls is 1/32, etc. Well, not exactly. Not exactly. I mean, yes, you can check. So you can check that this sum of the probability. The sum of the probability has to equal to 1. Let's check. The sum of the probability is equal to a half plus a quarter plus 1/8 plus etc. is 1 indeed. So it works. So this is works. So that means we've done something good. It looks like we're correct. Now we want the expected number. We want the expected number of girls. The expected number of girls is the probability times the number of girls times x. This is sum. So it's 0 times 1/2, 0 times 1/2 plus 1 times a quarter, 1 times a quarter. Yeah, you know this rule. Yes, so find the expected value. The expected value is 0 times a half, 1 times a quarter, etc. So 0 times a half, 1 times a quarter, plus 2 girls times 1/8, plus 3 girls times 1/16, plus 4 girls times 1/32, plus 5 times 1/64, etc. And that's what we are looking for, the question mark. Now, it's not that straightforward here because that's not the one we had. We have a sequence which looks like this. 1/4, so that's equal to 1/4 plus 2/8 plus 3/16 plus 4/32 plus 5/64 plus etc. Well, to answer this question, what we're going to do is we're gonna write this out like this. It's 1/4 plus 1/8 plus 1/8 plus 1/16 plus 1/16 plus 1/16. Yeah, because it's 3/16 plus 1 on 32 plus 1 on 32 plus 1 on 32 plus 1 on 32 plus etc. I'm not going to do 64. It just takes too much time, too much space. So what I've done is I've written 1/4 plus 2/8, which is an eighth plus an eighth, 3/16, which is 1/16 plus 1/16 plus 1/16. Now I'm going to rewrite it as 1/4 plus 1/8 plus 1/16 plus 1 on 32 plus etc. I've taken the first numbers. Now I'm going to take the second numbers. So plus 1/8 plus 1/16 plus 1 on 32 plus infinity up to infinity plus. So I've taken the second numbers. Now I've just the third numbers. So it's 1/16 plus 1 on 32 plus etc. Have I lost anyone here? So I've taken the first numbers, 1/4 plus an eighth plus 1/16 plus 1 on 32. Then I've taken the second number, so 1/8, 1/16, 1 on 32, etc. Then I've taken the third number, 1/16 plus 1/32 plus etc. So here it is. So the red ones are here. And the blue ones are here. Yes, very good. You can see that this is a geometric sequence. And this geometric sequence sums up to, well, it's 1/4 plus an eighth. It's this section of the geometric sequence. Like if you take away the first two terms, the first one term, sorry, you take away a half. So this is going to be a half. If you take this is going to be 1/4. And this is going to be an eighth. And then you go plus, etc. So the whole thing comes down to just 1/2 plus 1/4 plus an eighth plus etc. is equal to 1, because we already know that. So the expected number of girls in a family is 1. So on average, every single family will have 1 boy and 1 girl. Therefore, there will be exactly the same number of boys and girls. Now, this is the method I used. This is the method I used when I encountered this problem. Deep down, I understood that this is not the correct method, because when you go for an interview, they never give you something like that. That would be like you just don't have enough time, because what this takes you, like, I don't know, a good half an hour to work this out. They want a faster method, and the faster method is obvious. It's so obvious. It's just like there. So imagine all the children. Imagine all the births. Consider all the births in the country. All births in the country. And half of them will be boys, and half of them would be girls. And it does not matter what family they belong to. You just imagine a huge hospital. Yeah, half of them are boys, half of them are girls, and that's it. End of story. Quite frustrating, right? Quite unsettling that we've went through so much maths, and then we just realized, oh, well, it's the answer is right there. It stares you in the face. Well, imagine people having babies in the country. Imagine all the babies that were born in a given year. Half the babies are girls and half the babies are boys. So the country will have exactly the same number of boys and girls. It doesn't matter how many. It doesn't matter what the family wants. It doesn't matter what the government wants. It just is. No matter how many babies there are per family, if you take all of the babies, half of them will be boys and half of them will be girls. No? Does that not make sense? But that's what we are asking. The question, will the country have more boys or more girls? Basically, the the fact that each individual family has babies until they have boys does not affect the number of boys and girls being born in the country. It's the same. Now, you might have heard about an example where people wanted to have boys in reality. It's quite a gruesome story. But this wasn't just pure chance, unfortunately. Okay, fortunately for the girls, uh, there was the experiment in China that people were urged to have just one baby per family, and everybody wanted a boy because uh, well, because how it works, boys can provide for the family better, uh, and especially in rural areas where you need a lot of hard work needs to be done, a lot of manual labor. So families wanted to have boys and didn't want to have girls, and the we have more men currently in China than women, quite a lot more men because of that. But this is not. This is because the births were not purely to chance. I won't go any further on that. It's quite a gruesome topic, but yeah, people wanted boys, not girls, and that ended up not very well. So any experiments on humans shouldn't be performed. You can learn about this later on. Well, you can learn about it later. Okay, so yeah, that's what I wanted to talk about, the geometric and arithmetic sequences. You of course have the previous webinars to do, and if you don't fully understand, don't worry. Well, watch the previous David's webinar, which is amazing. Watch my webinar, which is not so amazing, but I believe it's quite good. They're all available on our YouTube channel. Taylor series. I just want to talk about the philosophy a little bit of the Taylor series. Like when you take your calculator and you do sine 30, and it's 1/2. Have you ever thought about how does it know? Did it learn every single sine of every single angle? That would be nonsense, because you can clearly, haha, yes, Archie, very good. Because the calculator, it is. The calculator can do operations, but it can only do certain operations. If you studied computer science, you know how addition works, easy. You know how subtraction works. You know how multiplication works, because multiplication is just uh, addition multiple times. You can work out division-ish. It's like a reverse multiplication, but it's still not very obvious, like how to divide, but you can do that in programming. But sine x, like how? The calculator doesn't draw a triangle with a given angle. It doesn't find the proportions, right? It doesn't do the or opposite over hypotenuse. It doesn't know what or like in the land of ones and zeros. How do you know what sine 30 is? Okay, you're welcome. And here comes the Taylor series. The Taylor series says that sine x is approximately x minus x cubed over 3 factorial plus x5 over 5 factorial minus x7 over 7 factorial, etc. The more terms, the closer the approximation is. More terms mean closer approximation. Well, you remember, you've learned that sine for small angles, for small x, sine x is approximately equal to x. That's it. That's where this comes from. Yes, small angles, small angle approximations. And this is just valid for any, and this is valid for any angle. Let's have a look. So here I'm going to y equals sine x. Here's sine x, perfect. And yeah, we're going to go y equals x. Ooh, look, for small angles, they are actually very close. They do look similar. Okay, like you have to zoom in to distinguish the two lines between. You have to zoom in really, really a lot in order to see a discrepancy. And only when you zoom in a lot, then you can see the difference. And the difference is in like the 4th decimal, whatever. So yeah, that's how close sine x and x are. I'll answer that question, Archie. Now, if you zoom back out and x minus x cubed over 3 factorial. And you can see that they are even closer. I might as well y equals x. I'll just leave y equals x here just to compare that they're closer. So you can see the blue line, which is a cubic graph, is closer to the red line than the green straight line. Y is equal to x minus x cubed over 3 factorial plus x to the power 5 divided by 5 factorial. And you can see that the purple line is even closer to the red line than the blue line. So as you get closer and closer and closer, as you get more and more terms, you get closer and closer and closer to the red line, which is the original function. Okay, so this is y equals x, y equals x. This is y equals sine x. This is y equals x minus x cubed over 3 factorial. This is y equals x minus x cubed over 3 factorial plus x to the power 5 over 5 factorial. So yeah, they're closer and closer and closer. Now, whatever your calculator has a finite accuracy. So if it sees that a number matches square root of 2 correct to 10 decimal places, it will say, oh, it's square root of 2. And you can test that. If you type in your calculator, so whatever the square root of 2 is, square root 2 is 1.41. So if you type in 1.4141356237, okay, you need more decimals. to 15 dp. This is a million digits, okay. 3 5 3 3 5 3 5 6 2 3 7 3 7 3 0 9 5 0 4 8 8. Ooh, I wonder why. Well, basically, you can get your calculator to think that is square root of 2. So it basically says if it's really close to square root of 2, it probably is square root of 2, and that's why when it gives you square root of 2. Maybe I have made a mistake, but there was even on a video on, I think it was the YouTube channel. What's it called? Maths. Number file. There was a video on number file where you type in some random stuff and it gives you pi because the calculator thinks it's pi. So yeah. Anyways, everything the calculator does is an approximation. It's a fundamentally has to be an approximation because your calculator is limited to 10, 14, 16 significant figures, and that's it. All right, so this is how the calculator knows what sine 30 is. It makes an approximation and finds the approximate value, which is never accurate. And you can find in Python, you can find some when you reach a limit on Python, you make division, and the answer is awkward. So Python inaccuracy. See. Right, error. I can't find it. Yeah, I don't remember the name, but basically you do an operation and it's like the answer should be 2, but it's actually 2.000000002, which is very, very, very weird. Anyways, derive the Maclaurin. So the Taylor series goes as follows. In the vicinity, vicinity of x equals 0, if a function is infinitely differentiable, f of x is approximately equal to f of 0 plus f prime of 0 embarrassing f prime of 0 multiplied by x plus f double prime 0 divided by 2 factorial multiplied by x squared plus f of divided by 3 factorial multiplied by x cubed plus etc. Yeah. Infinitely differentiable. That means infinitely differentiable. That means that it is you can find the derivative of the first, second, third, fourth derivative. So for example, there are functions where you can't find the derivative. For example, y is modulus x is not differentiable at x equals 0. You can't find the derivative. Derivative at x equals 0 at x equals 0, dy dx does not exist. So differentiable means you can find the derivative. So yes, sorry, the calculator does substitute, but not 30 because this is in radians, of course. So 30 degrees is approximately what? 30 is pi over 6 divided by 6, which is 0.52358 radians. So sine 0.52358 is approximately 0.52358 minus 0.52358 cubed divided by 3 factorial plus 0.52358 to the power 5 divided by 5 factorial, etc. And that's how sine 30 is approximately that. And if you put that into your calculator, you should get well, you should get 0.5. Well, yes. So yes, e to the power x is infinitely differentiable because you can find as many derivatives of e to the power x as you like. So e to the power x. So imagine that f of x is e to the power x. So f of 0 is 1 because e to the power, well, it's e to the power 0, which is 1. F prime of 0 is the derivative of e to the power x, is e to the power x derivative, which is e to the power x, because the derivative of e to the power x, well, yes, Archie, that's the point. You get more and more, you get closer and closer to 0.5. If you keep doing that, you will get closer and closer to 0.5. And then you get e to the power x when x is 0, which is 1. So f double prime of 0, using the same logic, is e to the power 0, which is 1, etc. And that means if you apply this formula, the Taylor expansion formula, so that means e to the power x is approximately equal, so f of 0, that's 1, plus f prime of 0, it's 1, so it's 1 times x, 1 multiplied by x, plus f double prime of 0 is 1, so it's 1 over 2 factorial multiplied by x squared, plus 1 divided by 3 factorial multiplied by x cubed, plus etc. So e to the power x is approximately equal to 1. Well, actually, it is exactly equal to, because we have infinitely many terms. No, okay, let's leave it. Let's leave it at approximately equal to 1 plus x squared over 2 factorial plus x cubed over 3 factorial plus etc. That's the Taylor expansion for e to the power x. So, for example, e to the power 0.2 is approximately equal 1 plus 0.2 plus 0.2 squared over 2 factorial plus 0.2 cubed over 3 factorial. So let's do the calculation. On your calculator, you do e to the power 0.2, which is approximately 1.2214. And this 1 plus 0.2 plus 0.2 squared over 2 plus 0.2 cubed over 6, which is 1.22133. So close, right? So this is this, and this is this. Differentiate the Maclaurin series. Maclaurin is the Taylor series when x is approximately 0. So you take Ex is approximately equal to 1 plus x squared over 2 factorial plus x cubed over 3 factorial plus etc. And I'm going to find the derivative. So e to the power x, you can find the derivative, is equal to the derivative of that. Well, the derivative of 1 is 0. The derivative of x is 1. The derivative of x squared is 2x over 2 factorial plus derivative of x cubed is 3x squared over 3 factorial plus, well, 4x cubed over 4 factorial plus etc., which is equal to, well, 1 plus 2x over 2 factorial. 2 factorial is 1 times 2, so it's just x. 3 factorial is 1 times 2 times 3, so 3 cancels and we get x squared over 2 factorial. 4x cubed over 4 factorial. 4 factorial is 1 times 2 times 3 times 4, so it's 1 times 2 times 3. So it's x cubed over 3 factorial, which is e to the power x. But we know that e to the power x derivative is e to the power x. So we've shown that the same works for the Taylor expansion as well. The function has to be infinitely differentiable in the vicinity of the point of which you are taking, well, you're approximating. Because from this graph, you can see that it works for x equals 0, but it doesn't work for x equals 4. Well, I mean, it does. It just, you need many more terms to make the approximation. The approximation is very good for x equals 0. It's not very good for x equals 4. So it has to be infinitely differentiable in the vicinity of the point of where you are looking at, if that makes sense. Okay, so that's e to the power x. Now, even more beautiful is that you can use a Taylor series within a Taylor series. Which ones? The Taylor and Maclaurin, or what? Okay. This is the formula. Where is it? This is the formula for the Maclaurin series. This assumes x is close to 0. The Taylor series does not make that assumption. The Taylor series works, assumes that the x is close to a. Taylor series. Taylor series assumes x is close to a. Any point. It works for any point. So for example, basically it's just a shift of the Taylor series. So that means f of x, when x is approximately a, is equal to f of a. Instead of f of 0, it's f of a plus derivative at point a multiplied by x minus a plus f second derivative divided by 2 factorial multiplied by x minus a squared. So basically, the Taylor series is just a substitution where you replace, well, the Maclaurin series is the Taylor series if you assume that a is 0. So because it looks simpler, and very often we need to find the approximation when x is small, plus etc. Okay. I'd love to talk about the Taylor series more, but let's stick to the Maclaurin for today. Okay, let's talk about the Maclaurin because I won't talk about the Taylor series in 2 weeks' time. So what in February, because most of the assignment is on Maclaurin series, not Taylor series. Differentiate. So we've differentiated that. The beautiful thing that for example, if we have this also works. It works because as x tends to 0, this thing also tends to 0. So because we say x is close to 0, and 2x minus x squared is also close to 0. So ex, as we know, is approximately 1 plus x squared over 2 factorial plus x cubed over 3 factorial plus etc. Now, if you have e to the power x, 2x minus x squared is approximately 1 plus 2x minus x squared plus 2x minus x squared over 2 factorial plus 2x minus x squared cubed over 3 factorial. We need up to power of 5. Oh, that's annoying. Plus 2x minus x squared to the power of 5. Oh, sorry, 4 over 4 factorial plus 2x minus x squared to the power 5 over 5 factorial. Actually, not so bad. I don't think that's too bad. So let's have a look. So that's going to be equal to 1 plus 2x minus x squared plus 4x squared minus 4x cubed plus x to the power 4 divided by 2 factorial plus 8x cubed minus 6x to the power 4 and the next one is going to be x to the power 6, which we don't need. Is it? Oh no. No, it's going to be x to the power is going to be x to the power of 5. So it's going to be plus no, that's not 6, that's 12. That's 12. Sorry about that. So plus 6 x to the power of 5. And we don't need the rest because the next one is going to be power 6. So divided by 6 plus this is going to be 16 x to the power of 4 plus 4 multiplied by 8x cubed, 8x to the power of 5 with a minus divided by 24 plus, and this is going to be 32x to the power of 5 over 5 factorial. So I'm skipping all the powers greater than divided by 120. And then it is just a matter of simplifying. But the point is that it doesn't just work for e to the power x. It works for everything like e to the power e to the any power as long as that power is 0 when x is 0. So it works for e to the power sine x because we know sine x is approximately 1. What? No, it's not. It's x minus x cubed over 3 factorial plus x to the power 5 over 5 factorial. And e to the power sine x is going to be 1 plus x minus x cubed over 3 factorial. You know what? It's going to be like this. Plus squared over 2 plus cubed plus 4 factorial or etc. Okay. Yeah, it wouldn't work for e to the power cos x, but there's a way around it. It would work for e to the power 1 minus cos x, for example. It would work for e to the power 1 minus cos x. So yeah, that's really cool because all you need is just a substitution, a very straightforward substitution. I don't have time to do this, but I'll do this one. Limit of x tends to 0 as sine x over x. Now, if you directly substitute, sine x is 0 and x is 0. So you do 0 divided by 0. That doesn't make any sense. But because x is close to 0, that means we can use the Maclaurin expansion. So sine x over x is approximately x minus x cubed over 3 factorial plus x to the power 5 over 5 factorial plus etc. divided by x, which is equal to 1 minus x squared over 3 factorial plus x 4 over 5 factorial plus etc. divided by x. But x tends to 0, so the whole thing, this tends to 0. Tends to 0 because x tends to 0 and 1 is 1. So this is equal to 1. The limit of sine x over x as x tends to 0 is 1, even though you have 0 divided by 0. Okay, in a similar way, the rest is done in a very similar fashion. I really hope it was useful. I really hope I didn't lose you halfway through. I hope you enjoyed it. If you are struggling to understand Taylor series, do watch the other webinars and do watch the videos that we offered you as part of the assignment. There's some really nice stuff going on there. And oh, I'm so sorry. I've prepared a massive question for you, and if I got to put it in, it's right here. I've spent some time preparing it. I will have to do it next time. Well, then I'll see you next week for some physics, and the week after we'll do maths again. All right, see you everyone. Bye.